Very interestingly, tensor operations have geometric interpretations. We will also look at how deep learning has a geometric interpretation, but let's start with the geometric interpretation of tensors. The contents of the tensors manipulated by tensor operations, that is, if I have x, I perform operation A, and let's say I get x minus x dash, can be interpreted as coordinates of points in some geometric space. This implies that all tensor operations have a geometric interpretation. Now, we may not be able to visualize all of them because of our limitation of only being able to visualize 3D or less than that. But for the sake of understanding, let's take a very simple example. Say a equals 0 0.5 comma 1 is a tensor. Let's say it's a vector. Then we can picture the vector as an arrow linking the origin to the point. So here's my point, a 0 0.5 comma 1. So in x-axis I have 0 0.5 and in y-axis I have 1. Now we can add a new point to the same plot, b equals 1 and 0 0.5. So b equals 1 and 0 0.5 will be over here. So here's our a, this is my a, and this is my b. So if I add b to a, that is, if I want to calculate a plus b, the sum will be, in x-axis, a already had 0.5 and b had 1, so 1 plus 0.5. In x-axis, we have 1.5, and in y-axis, we have a had 1 and b has 0.25, so this becomes 1.25. So a plus b is a new point over here. And we can imagine that the sum of a plus b gives us a new vector that looks like this. So sum of a plus b is a new vector whose magnitude is longer than a and b and whose direction is in between a and b. And this represents the sum of the previous two vectors. So we can imagine that geometrically, when we add these two vectors, we are adding a with b to obtain a new vector, which is a plus b. So this shows how tensor operations can be interpreted in a geometric way, geometric interpretation of tensor operations. Now, this means that elementary geometric operations, such as affine transformations, when we say affine transformations, we mean rotation, mirroring, scaling, translation, shearing, non-uniform scaling, all can be expressed as tensor operations, which means if you have image data, then we can say take the image data as input. I can do some tensor operations, some tensor operation to this image and obtain a rotated image. I can similarly do mirroring, I can scale it, make it bigger, I can translate it, maybe shift the image up and down, left and right. I can even shear it and do other things. What I may not be able to do is non-affine transformations or non-geometric operations. For example, say I have image and say I want to take one corner out and put it into this corner, or say you have a complex algorithm, that can only do this, then these may not be directly achievable with tensor operations. For instance, to rotate a 2D vector by an angle theta, this can be achieved via a dot product with a 2 by 2 matrix. So say you have a picture right? And what we want to do is rotate it so that it looks something like this. Then we can simply perform a dot product of this matrix, let's say x, with another matrix r equals u v, such that u is cos theta, comma sine theta, and v is minus sine theta, comma cos theta. So you can play around with it and see that depending upon what value you provide provide as theta, you can rotate an image or any other random 2D numpy array. You can even create a random 2D numpy array with certain values in it and see if rotation works or not. What this leads us to think is that deep learning overall is nothing but geometric transformations or chain of geometric operations. In this way, we can imagine a geometric interpretation of the operations that we do in deep learning. This is because neural networks consist entirely of chain of tensor operations, and that all of these tensor operations are just geometric transformations of the input data. So they basically scale, shear, rotate, and do other things. Overall, we can interpret a neural network as a very complex geometric transformation with maybe various steps or various layers of transformations in a high dimensional space implemented via a long series of simple steps. Now, to understand an intuition about what this basically means, imagine two sheets of colored paper, one red and one blue. So say we have two sheets of colored papers. Here the picture shows more than two, but just let's say we have two of them. Put one on top of the other and crumble them together into a small ball like the one shown over here. So this one, we have two colored sheets crumbled together into a single ball. The crumbled paper is your input data. So this is my input data, and each sheet of the paper in the data is the class of the data or the classification. So maybe the color orange represents a cat, and this color maybe represents a dog. And in the input data, it is unclear which rows represent a cat and which rows represent a dog. And what a neural network basically does, machine learning basically does, is machine learning, so this shouldn't be here. Machine learning basically does is takes this data and uncrumble it so that the two classes are separable again, so that we can say this is dog and this is cat and so on. So the point here is that from our input data, looking at what the column values are and the row values are, it may not be clear what class this first row belongs to and what class the second row belongs and so on. The task of neural network is to somehow uncrumble this information so that machine learning can classify what class each data point belongs to.